We'll do a brief video here on 4.6, integration by substitution, and we'll start off with these two warm-up problems. If you haven't had a chance to look at them yet, why don't you just go ahead and pause the video, and then the answers will be here waiting for you. All right, now we move on to kind of pattern recognition and examples. So let's take a look at the warm-up, the second problem, but let's just change it slightly. You know, it was a little cumbersome to do it the way it was presented. Could you imagine what it would be if we had to deal with this, not as a squared, which at least we could deal with, but the seventh power, right? Obviously, we wouldn't want to expand this to the seventh power. So the good news is there is an alternative method we could explore. Here's what you want to notice, though. The 8x that happens to sit in that problem happens to be a derivative, right? It's a derivative of 4x squared plus 1. Not all to the seventh, but just that internal quantity. That is the key to the method we're about to use, right? So what we want to do is we want to always visualize the integrand, and that's the whole thing inside the integral there, right, as a product of a differentiable, right now, power function. That's really what we're dealing with. And its derivative. So that's the key. Can I visualize this stuff as the product of a power function and its derivative? Because if I can do that, then the whole idea is I could use this substitution method. So what does that look like? Well, here's the deal. Let's suppose we let u, I'm just picking a random variable here, equal 4x squared plus 1, right? Well, du dx, the derivative of u with respect to x, would simply be 8x. And like I said before, it's no coincidence that 8x happens to be in the problem. Now watch this. By simple substitution, if I were to come and rewrite this integral and say, well, instead of doing 4x squared plus 1 to the 7th, how about I call it u to the 7th? But I haven't really accounted for that 8x dx, right? Well, let's come back up here. What if I made du equal 8x times dx by just a little algebra there, right? Multiply both sides. Well, now I can make this integral read u to the 7th du. In which case, all I've done is I've created a simpler integral in a different variable, and when I integrate that, I just get u to the 8th over 8 plus c. Now, I can't leave that as my answer because the original problem didn't start in terms of u. So, what do I want to do? I want to go back in, I want to account for that u and say, well, the real answer would be 4x squared plus 1 to the 8th power over 8 plus c. So the whole key there was that we were lucky enough to have the derivative of 4x squared plus 1 in the problem itself, in the integrand. That's what we'll be looking for as we do a couple more examples. Okay, let me do example 1 with you as well. So, same idea, right? If I can identify 2x minus 3 as some quantity, let's call it u, right? It just so happens that the derivative of u with respect to x is 2, which I also see in there. But to create the substitution I need to basically write du equals 2 dx. Basically multiply that dx to the other side, right? And then this allows me to come in here and say, well, what if I looked at this integral not as the way they proposed it, but as u to the 3rd times du? Now, that allows me to just say, oh, okay, well, that's a simple power rule, so I get u to the 4th over 4 plus c, and of course I want to switch back now and say the real answer would be 2x minus 3 to the 4th over 4 plus c. So as you can imagine, there's a whole host of functions and their derivatives and how the way they are presented. That's where it could be a little bit challenging. So just this simple idea, why don't you pause the video, try example 2, and then I have the answer waiting for you on the next slide. All right, as promised, here you go. Example 2 should end up as e to the negative 3x. Now the idea here is finding out that it was the exponent here of negative 3x that was the u, because that guy's derivative is negative 3. So we're going to continue to see different things, trig functions, all sorts of things. Okay, let's try another one together. So example 3. Here it's a little bit difficult, but if you think about what we said in terms of the pattern recognition, it's recognizing a function to a power and its derivative. So thinking, oh, okay, well, here's the deal. I'm going to make u, right, equal to sine x. Well, that would be an incorrect choice here, because the derivative of sine is cosine, not cosine squared, right? And we don't want that. So let's erase that. And let's think again. What if we made u equal cosine of x? Not to the second power, just cosine of x. Well, du dx would be negative sine x dx. Now, this is interesting because we haven't seen this yet. We're off by this constant here, right? Well, I can put the negative here, right? You say, well, you're not supposed to do that. I agree. So I would balance it out by putting a negative 1 here, because a negative times a negative is a positive. I'm right back to where I started, right? So when I rewrite this in substitution, what about if I wrote this? Negative 1, right? Here's my integral, u squared. And then think about it. Now that I've inserted that negative sine x dx, that is du. So everything matches. There's a one-to-one match here. The u is taken up by cosine of x. The square didn't go anywhere. The negative sine x dx is really negative 1 in du. And so if that doesn't help, if you're saying, wait, that seemed like a little, some type of slight magic there, it doesn't seem to add up. Let me kind of show you another way to think about this, right? Here's the original integral. Cosine squared x sine x dx. Okay. Well, again, if I'm making u cosine of x, and du is equal to negative sine x dx, right? I want you to think about this. Here's sine x dx. If I were to quote-unquote solve for that, you would divide both sides by a negative 1, right? And so this truly is the substitution you're making in place of sine x dx, right? So this is being replaced by negative 1 du. And all I'm doing in this, the way I phrased it originally, is I'm just putting that negative 1 outside the integral. So we may have to talk about this. That's not exactly the easiest thing to catch. But the idea here then is if I'm ready to roll, my answer is negative 1 u to the third over 3 plus c. And my final answer, of course, is negative cosine cubed of x over 3 plus c. So this idea of we're off by a certain constant factor, something we have to look into. So try example 4 and example 5, and you'll see something similar and see if you pick up on it. Okay, pause the video, and the answer is waiting for you on the next slide. Okay, here's example 4. You can see our final answer right here. We were, again, off by this negative 1, so I had to make this substitution on the outside of the integral here. And then for example 5, this time we were off by a constant of 5. So again, the idea is if I'm trying to replace cosine 5x dx and make an equal substitution, then look down here. I would have to divide both sides by 5, and then therefore that's where the 1/5 comes in. The du is just in a different place. The 1/5 is a constant. We can take constants out of the integral. So I'm sure we have plenty of questions. We'll address them as soon as we get back into class. But at least this is a good starting point.